Application of prefabricated retaining walls with increased shear resistance to ensure tailings dam stability. Authors: Radomir Timchenko, Dmitry Krishko, Volodymyr Kozariz, Oleg Nastich, Oleksii Tiutkin. Accumulation of a significant amount of industrial waste is associated with the development of the mining and metallurgical industry in Kryvyi Rih. The volumes and areas of production sludge and concentration tailings have grown considerably over the long term of operation. This negatively affects the state of technological and environmental safety and worsens the environmental situation in the adjacent areas. Tailings ponds and sludge storage facilities do not currently meet modern standards that regulate the requirements for operational safety, reliability, stability, and durability as they were designed in the last century. Application of retaining walls is proposed to prevent or avoid the negative engineering conditions of dams and embankments. The development of new design solutions for retaining walls and calculation methods for determining the lateral pressure of multilayer backfill is an urgent scientific task. The operation of tailings and sludge storage facilities is the subject of research by many world-class scientists, namely Emily Lane, Matthew Kryman, Benjamin K. Sovakol, Donald East, Ruben Fernandez, Carlos Caxiutlo, Alvar Pastor, Patricio Valderrama, Edison Atencio, John Waits. Authors who made a significant contribution to the development and improvement of retaining wall structures and methods of their calculation include I. P. Boyko, A. Y. Budin, B. F. Horyanov, V. B. Hurovich, M. P. Dubrovsky, V. S. Zelensky, M. L. Zutsenko, U.O. Kiricek, H. K. Klein, V. D. Kostyakov, O. Petrikov, M. B. Poizner, V. H. Taranov, R. O. Timchenko, V. H. Shapoval, V. B. Shvets, P. I. Yakovlev, etc. The aim of the research is to ensure the stability of tailings dams by using the proposed prefabricated retaining walls with increased shear resistance during the multilayer backfill buildup and operation of the structure. To achieve this, the following tasks should be solved. To conduct an analytical review of the schemes and designs of tailings dams. To conduct a comparative analysis using the recommended methods to determine the safety factor for the calculated sliding curves. To develop a new design of the retaining wall to ensure the stability of the enclosing dams. To formulate new principles for determining the horizontal pressure on the retaining wall, considering the multilayer backfill and the load on the surface. In recent years, significant experience has been gained in the operation of storage facilities and the construction of dams and embankments made of waste and overburden. Any type of storage capacity, except for pit and basin ones, requires the construction of enclosing dams or embankments that are washed from waste materials or filled with overburden or local soils. Depending on the technical conditions, enclosing dams or embankments can be built to their full height at once or in stages. Myrolubivka Tailings Pond is located on Velika Krokva Gully, its slopes and adjacent areas. Velika Krokva Gully flows into Hrushavada Gully. The area around tailings ponds is built up with technological facilities and communications. Temporary man-made, rock-filled and hydraulic formations, such as waste dumps, walls of embankments and dams, roads, sludge and tailings ponds, etc., play a significant role in the geological structure of the area. These formations are often tens of meters high. To control the quality of the washed and tailings, the Geotechnical Control Service, GCS, took 185 samples in 23 boreholes, figure 1, on the beaches at the dike at the 140.0 m level. Based on the results of the measurements, graphs of subsidence are built, figure 2, figure 3. Based on the results of the measurements, graphs of subsidence are built, figure 4, figure 5. To monitor the depression curve, water levels are measured quarterly in piezometers, figure 6, installed on the dams at 115.0 m, 120.0 m, 125.0 m, 130.0 m and 135.0 m crest levels. Strength and stability of modern hydraulic facilities are assessed by the limit state method, according to which all the initial design values, which are random in nature, are represented by some deterministic values, and the impact of this variability on structure reliability is taken into account by relevant coefficients regulated by the standards. In determining the dam stability in the vicinity of spillway structure 3, the following design case is considered. As for the main load combination, the dam has a 125.0 m crest, a normal retaining level, 123.5 m, in the upstream, and filtration in the dam body. The dam stability is calculated by two programs, the Computer-Aided Design System for Ground Hydraulic Structures and the KZU-86K program developed by specialists of the Vyazem Institute, the All-Russian Research Institute for Mineral Deposits Drainage, Protection of Engineering Structures from Flooding, Special Mining Works, Geomechanics, Geophysics, Hydrotechnics, Geology and Mine Surveying. The Computer-Aided Design System for Soil Hydraulic Structures, CAD-SHS, is designed to solve a number of problems in designing dams, dikes, upland ditches, sludge ponds, tailings dams and other structures. The software allows performing stability calculations using the following methods. Terzaghi weight pressure method. Mazovitanov method of inclined interaction forces, recommended by the standard. FEM, the finite element method. The KZU-86K program. Filtration calculations are performed using the FEM method based on the methodological recommendations for calculating the safety factor of slopes with a circular cylindrical sliding surface using the KZU-86K program. The program allows defining a set of design slip curves, with safety factors, in a given slope range. This makes it possible to define both general and local slip curves. The results of stability calculations are expressed as slip curves on the cross-sections of station S, 39 plus 00, downstream slope, figure 8. The results of calculations of the stability of the downstream slope of the dam, with the selection of the minimum safety factors determined for the local curve, are shown in the design sections and summarized in Table 2. Analysis of the actual condition of hydraulic structures, taking into account the calculations performed, drawing the following conclusions about Myrolubivka tailings storage facility. The reliability of the downstream slope of the tailings dam at Myrolubivka tailings storage facility is assessed in accordance with regulatory requirements. Most calculated cross-sections, according to all the methods used to calculate the downstream slope, have a safety factor, both for general and local stability, that is higher than the minimum required by the standard. For certain cross-sections, minimum safety factors determined are less than the required standard values. For these sections, additional measures to ensure standard stability are required. According to the standard, Krivi RIH is classified as an area with a seismic intensity of 6 points. Soil conditions at Myrolubivka tailings pond are classified as Category 3. At the same time, the overall seismicity of the area is 6 points and it does not fall within the seismicity standard. On this basis, no seismic stability checks are performed at this stage of work. Recommended measures include: all hydraulic structures of Myrolubivka tailings facility should be subjected to constant monitoring of the dam condition, compliance with design requirements for tailings allocation technology, the degree of wear of pipelines, especially those passing through dams and in the vicinity of hydraulic structures, and compliance with design water levels in the tailings facility. To ensure the required reliability of the tailings facility, it is proposed to construct a special type of retaining wall in the area with the lowest safety factor for the period of dam operation. The proposed prefabricated block-type retaining wall, Figure 9, Figure 10, consists of a foundation slab and a vertical element presented in the form of concrete or reinforced concrete blocks mounted on top of each other. The front face of each of them is made straight, and the back face is in the form of a structural surface of pyramids. The foundation slab of the retaining wall is equipped with piles located directly under the base of the foundation slab. To prevent premature filling of the cavities, two flexible separating sheets of elastic and pliable material made of a biodegradable polymer are placed on the back surface of the vertical element. The proposed structure can be used to stabilize unstable slopes, while the foundation slab, piles, and vertical element blocks can be unified. It is highly reliable when operating in a critical situation of an unforeseen emergency increase in the shear force load. The installation of this structure will provide additional stability of the hazardous area of the tailings pond and will guarantee the reliability and operational longevity of the tailings pond. Figure 11, Figure 12, Figure 13. Figure 11. Retaining wall area. Figure 12. Installation of a prefabricated retaining wall. Figure 13. Flooding area in case of a potential failure. The paper analyses experimental and theoretical studies of distribution of sliding planes in multilayer backfill of retaining walls in the absence and presence of different strip loads on this surface. These studies indicate that horizontal shear of the entire wall or any of its upper parts leads to the formation of a single shear plane under not only complex but also concentrated loads on multilayer backfill. Moreover, this effect does not depend on the sequence of layers with different physical and mechanical characteristics phi and gamma along the backfill depth. Adoption of a single sliding plane for each depth of the retaining wall allows presenting a calculation scheme for determining the horizontal pressure, Figure 14, and formulate new principles for determining the horizontal pressure on the retaining wall, taking into account the multilayer backfill and the load on the surface in accordance with the standard. Myrolubivka Tailings Pond is an engineering structure of the first category of responsibility and currently requires new approaches, as well as changes in technology to ensure its stability during long service life. Available calculation methods based on the theory of linearly deformed media do not fully meet the operating conditions. Therefore, consideration of the influence of a multilayer nonlinearly deformed massif under external loading allows formulating new principles for determining the horizontal pressure on the retaining wall, namely, the mass of sewing between the wall and the shear plane is divided into separate prisms resting within each layer high on the collapse plane. The prisms are divided by vertical planes extending from the intersection of the collapse area with the boundaries of the soil layers to the backfill surface, in areas of loaded surface, or to the footwall of the local load. Part of the distributed load located on any prism is summed with the weight of this prism, i.e. included in the value GI. Interaction of prisms along vertical planes is not taken into account. Each depth has its own collapse area, the position of which does not depend on the total wall depth max. Application of a special type of retaining wall allows obtaining an economic effect due to both the design solution and the extension of the service life. The effectiveness of the existing system for protecting the aquatic environment, primarily groundwater, from pollution by the Myrolyubovskoye tailings dump in the area under consideration is estimated at 87%. Thank you for the attention.